Hi, everyone. Thanks for joining us for this talk today. Today, we are going to have a talk on multiscale, multiphysics, and data-driven modeling framework for subsurface energy geotechnics by Dr. Zhang. Let's listen to like a small abstract for that. The net zero emission goal in 2050 is driving a paradigm shift in the oil and gas industry to improve their environmental, social, and governance performance. Oil sands in Alberta will still play an important role in providing a sustainable energy supply as solar, wind, and hydraulic power are subject to natural temporal fluctuations. The success of CO2 capture, storage, and utilization project demonstrates its potential to be promising carbon mitigation technology and play an important role in economic growth and employment in the transforming energy sector. Dr. Zhang's talk will focus on a multiscale, multiphysics, and data-driven modeling framework for subsurface energy geotechnics. The multiscale component is a development of elastic and plastic numerical upscaling techniques and extending them using machine learning techniques for improved computational efficiencies. The multiphysics component is the implementation of upscaling techniques to coupled thermal hydromechanical simulations. Therefore, it's possible to optimize the production performance while also ensuring caprock integrity for in-situ recovery of oil sands. The data-driven component is focused on the development of surrogate models using deep learning and pathways using the surrogate models for uncertainty quantification and optimizations for geological CO2 storage. Dr. Zhang is an assistant professor at the University of Alberta, where he obtained his Master of Science in Petroleum Engineering and PhD in Geotechnical Engineering. He is a registered professional engineer and has been leading and involved in a variety of projects in subsurface energy geomechanics. Dr. Zhang is currently the principal investigator for several research projects funded by the Natural Sciences and Engineering Research Council of Canada, Alberta Innovates, and UAlberta Future Energy Systems that focus on experimental and numerical investigations of thermo, hydromechanical, chemical response from pore to field scale, multi-scale modeling and simulation of subsurface energy developments, and data-driven decision-making in in-situ recovery and open-pit mining of oil sands, CO2 storage and utilization, and geothermal systems. Let's have Dr. Zhang here. And yeah, let's start.
Yeah, thank you so much for the kind introduction, Athena. It's great to be back. I remember the last time I presented here for geotechnical seminars 3 years ago, and everybody is in quarantine. Yeah, now I'm back, and great. It's great to see my supervisor for my PhD is in the room, and he has been supporting a lot of work in this talk. And Nathan, I'm glad to see you here. And he is the second author for two of my papers on our papers on elastic and plastic upscaling. And good to see the new faces, majority and new faces. Great to see that. So yeah, my talk today is about mainly the research ongoing in our research group, which is mainly focused on the multiscale and multiphysics and data-driven modeling framework for subsurface energy geotechnics. So try to find a way to move my slide. Okay, so slow unloading. So this is outline for my presentation. First, I will go through the importance and the challenges for the above mentioned multiscale multiphysics and data-driven modeling framework for subsurface energy geotechnics. And there will be three components for my talk, which is multiscale. What does that mean? Is in our research, it's a numerical and machine learning enhanced flow geomechanical upscaling technique, considering geological heterogeneity, which includes lithology heterogeneity and also some discontinuities. And multiphysics, which is the coupled thermal hydromechanical simulation and the application in evaluating the caprock integrity during in-situ recovery of oil sands. And data-driven has been a new component in our research theme, which we want to do the optimizations and uncertainty quantifications for decision makings in subsurface development. So I will show two case studies. One is SAGD, and another is geological CO2 storage as examples. Yeah, a lot of you probably have seen this. So future subsurface energy system is not going to be only focused on the traditional oil and gas industry. So we will have more components like geological carbon sequestration, which we inject the supercritical CO2 in the saline formation. And a lot of others are looking at depleted reservoirs, and CO2 leakage is going to be a huge thing, right? And also there are a lot of shale gas that is going on in the Duvernay and Montney formation. So the hydraulic fracturing is a big component. And also the enhanced geothermal system will also require that to increase the hydraulic conductivity in the reservoir. And in the reservoir geomechanics research group, they are also working on nuclear waste repulse rates. Nathan showed some good experimental tests on the rocks that has 1 nanodarcy, 10 nanodarcy permeabilities. Those are also very important. And also energy storage, including hydrogen, compressed air, and maybe methane. And that is also important. And the caprock integrity will also be an important component in the future subsurface energy system. Okay, I will still use the oil sands as an example to start my talk. And we all know oil sands in Alberta, it has almost 10% of the total reserve globally. So if you consider that 97 of the oil in Canada is actually oil sands. And oil sands has its definitely has its features, which is high viscosity. So it's almost it is in a solid state at room temperature. So other than open pit mining, that we can definitely mine the oil sands that are just about 75 meters deep. When it's go beyond the 75-meter deep, it becomes uneconomical to really do the open pit mining. So that's why we need to do the steam-assisted gravity drainage or cycle steam stimulation, which is the in-situ thermal recovery to produce oil sands. So I will just use SAGD as an example, just for people who are mainly focused on mining or focused on the traditional geotechnical engineering, just some background information. So we inject hot steam, which is around 200 degrees Celsius, into the injector. That is just 5 meters above the producer. Usually there are 2 horizontal well paths in the well paths for SAGD. And then the latent heat of the steam will heat the bitumen around, and slowly the bitumen will become mobile because the viscosity of it decreased a lot, even 6 magnitudes due to the increase of the temperature. Then the gravity will drive the bitumen to produce production well. And as you can see here, this is the steam chamber that is formed with the high pressure, high temperature steam, which is in the subsurface. And as we all know, because of buoyancy effect, steam will just keep going up and going up. And at a certain stage, it will just push the caprock, which is mainly the Clearwater shale in Athabasca oil sands. And that will require us to have a continuous caprock, as it shows here, in order to maintain the safe operation of oil sands, right? So that means the caprock integrity is really important in the in-situ recovery of oil sands. Okay, and as Dr. Rick is here, and one of his students, Ali Khani, works on the Jocelyn Creek steam release incident. And he finished his PhD back in 2022, if I remember correctly. And he is now working for CNI. I don't know whether he is online today. And let's talk about it. Actually, this happens back in 2006 at the north of Fort McMurray, when Total Energies started their steam circulations to start their SAGD production. And actually, they inject the steam at very high injection pressure, according to its depth, which is just around 150 meters. They inject at around 1.8 MPa. And that actually leads to caprock failures. And we could see here a very large surface disturbance, which is 165 meter by 65 meter, which is more like a football square, right? And that caused a lot of environmental issues. And also, as we know, when we create those big craters, we basically break the caprock. That means the steam cannot stay there in situ. So that's why Total Energy has to abandon the entire Jocelyn Creek project in 2010 for this catastrophic steam release incident. Okay, that actually demonstrate the importance of the energy geotechnics in Alberta oil sands. And after that, definitely the regulators start to look into the problem on how to better regulate this kind of operations in oil sands and avoid those problems. So they have this directive 086. They released that back in 2010. Then they keep modifying it. And this is the version back in 2020, which is called the Reservoir Containment Application Requirements for SACD project in the shallow Athabasca oil sands. And the definition for the shallow oil sands is basically when it's above 150 meters. Okay, so as we can see here, Alberta regulator, they for the last 15 years, they require all the new or amendment to shallow SACD must ensure the caprock is continuous and thick, and also geomechanical modeling has to be conducted for both the maximum operation pressure, considering the factor of safety for both tensile and shear failure. And also, they have to establish risk assessments and monitoring program for the SACD project that is operating in the shallow formations. And actually, Dr. Rick has a talk back in 2021, if I remember correctly, in Energy Simulation Summit about this caprock safety. And it's available on YouTube if you're interested. Just go for it. It's one of the go-to talk for caprock integrity. And here, I just want to pave the foundation for the importance for subsurface energy geotechnics. So in our group, we want to focus on the challenges in a more broader scale, but still we will go back to the case studies for SACD. So the mainly focus on three challenges, which is the geological uncertainty. That is the first thing, because all of the reservoirs, geological reservoirs, they are going to be very heterogeneous and isotropic. Okay, so if you look at the geological sequence, it's because of the positional environment is usually more continuous in horizontal direction, but actually very isotropic in the vertical direction, right? And for the well data that we have, as you can see here, this is a drilling holes for mining project, so it's more dense. But actually for most of the reservoir project, it's going to be very sparse. So we only have very limited well data. So that's why we need to use probabilistic modeling using geostatistical method to generate different realizations of the reservoir to consider the geological uncertainty. That's our first challenge. How do we consider the impact of geological uncertainty in subsurface modeling and simulation? And second is because most of the cases, like in SACD and geological CO2 storage, there is going to be a lot of thermal hydromechanical interactions involved, and maybe geochemical interaction, and started to also track a lot of attention right now. And let's still use SACD as an example. This is actually the Sanko-Mackay River I took from the AER report back in 2017. As we can see, it doesn't show the legend here, but we can see the red here is actually the monuments showing the surface cave. And that is going to be around 70 centimeter. If you consider, if you have a facility above that, you need to be careful. And also 70 centimeter surface cave means there is a lot of pressure that is pushing the surface, right? So thermal expansion is going to be a very huge problem. And also the shear induced porosity and permeability changes is also important in both of the reservoir because it may increase the permeability, but it may also pose a lot of risk on the caprock if we generate a lot of fractures inside of it, right? And the third problem is definitely computational efficiency. So in order to solve those thermal hydromechanical, if we want to chemical inside of it, there is a lot of high order equations that need to be solved in 3D. And for field 3D model, usually it has more than 1 million grid blocks or even 10 million grid blocks in order to really capture the details of heterogeneities in the reservoir, right? And because of that geological uncertainty, we also need to generate a lot of realizations. And in order to run those realizations, to do uncertainty quantifications, it needs a lot of computational time, right? So those are the three challenges that we are trying to focus in our research: geological uncertainty, THM interactions, and also trying to solve the problem of computational efficiency. Okay, yeah, this is when we are happy back in the Lunar New Year in 2023, and we haven't got any chance to really gather together in 2024, and probably during the summer, let's have a barbecue. So yeah, these are the research themes in GeoCloud, and I will consider those two as the foundations for the research, which is a multi-scale investigations of flow geomechanics response from pore to field scale, and also coupled multiphysics, which mainly focus on THM simulation, and also data-driven decision-making for subsurface engine development, where we really establish good tools for multi-scale and multiphysics simulation. So we can run a lot of simulations, generate a lot of data to compare that with the monitoring and also the field data for decision makings in both SAGD, geological storage, CO2 storage, and also hydrogen storage, you can name it. Okay, let's start first. What is multi-scale investigation of flow geomechanics response from pore to field scale? So let's first look at this slide, which explains the heterogeneities from the pore to field scale. As you can see here, oh yeah, heterogeneities definitely could even go back to the nanometer. It is also possible. And make it simple, I start with micrometers, and that's usually in the pore scale. And at different pores, in the pore scale, if we look at sand, silt, and clay, we will probably find that the grain distributions are very different. And that will also generate different pore structures. And those pore structure heterogeneities is really, really important for us to understand the pore structure changes caused by deformation and failure will alter the tortuosity in the pore space, and also lead to absolute and relative permeability of the rock and so on, right? But right now, we're not diving very deep into the pore scale. We are more focused on the continuum scale, which will finite element modeling, finite volume modeling, or cohesive zone modeling are used for both continuous and discontinuous modeling. So yeah, and if we look at the core scale, this is one of the photo core image taken from Alberta Energy Regulator. We can see in the reservoir, especially in the oil sands, we have a lot of shale beddings that is interbedded in the oil sands, right? And we also know that most of the constitutive models and geomechanical properties are actually determined by the core scale experiments, right? But how do we really use that in field scale? That's a big problem, right? So that's why we're developing the upscaling techniques, trying to upscale our understandings of those core scale measurements in both constitutive models and geomechanical properties, and use that in the field scale reservoir geomechanical simulation, because that is definitely needed for assessing the geomechanical risks in both of the slope stability during the open pit mining, also caprock integrity during in-situ recovery of oil sands. And this is a slide I show a lot for the motivation for upscaling. And we can see that the reservoir is very heterogeneous, and that will lead to non-uniform steam chambers, as it shows here. And we also receive a lot of very irregular well production data, and that may even lead to problems like caprock integrity in Jocelyn Creek. So ideally, we want to start with the geological model that has a lot of wells that we generated for Mackay River. And that definitely will lead to a lot of uncertainties because we don't know all the information in the reservoir. And we can generate a fine scale geocellular model that could be centimeter scale in thickness. It could even be centimeter scale horizontally, but that it won't be very computationally efficient. So usually the grid blocks are more like 50 meter by 50 meter, 100 meter by 100 meter, if we want to have a reservoir that is a kilometer by kilometer. So that means we have to do the upscaling to reduce the grid numbers to make our model more computationally efficient. And also, in order to run a lot of realizations for uncertainty quantifications, we have to reduce the number of grid blocks. And then we can do the reservoir geomechanical simulation and use that to inform the decision-making for both production in enhanced oil recovery and also caprock integrity for safety management. So this is a timeline for our flow and geomechanical upscaling development. So I mainly focused on flow-based upscaling during my MSc, which I won't discuss today. But during my PhD, when I'm working with Dr. Rick and Dr. Deisman and also Dr. Bovell, we developed both the numerical elastic upscaling, numerical plastic upscaling. And during the postdoc, we further extend that into an in-based upscaling for shear strength. And now we also have a CNN-based upscaling for stress strain responses. I will feature those 4 papers in the upscaling. So let's first look at the framework for machine learning enhanced upscaling. So when we have a lot of core samples, ideally, we want to do a milling experimental test, which is a Traxel test, which is each one will take more than 2 hours or even a day or 2. That won't be realistic, right? And we all know, in order to do machine learning, we need a lot of training samples, right? How to really bury those gap here. So that's why we want to generate a lot of realizations based on the core images and also in the reservoir. And then we can calibrate the experimental test. Then based on the calibrated model, we can run a lot of numerical simulations. That is much faster compared to do the experiments. Then we can feed that as a data set for the CNN proxies. Then we can generate the CNN proxies that can be used for both estimating the shear strength and also the stress strain response. And then problem comes. In the traditional, now node simulator can directly take CNN models, right? It can only take the constituted models that they defined and also the geomechanical properties you defined inside of it. So how do we really bridge this gap? So one of my MSc students, Xiaoyan, she actually find a way to calculate the upscaled properties based upon the CNN-based stress strain responses and also the volumetric strain changes as a function of axial strain. So then we can generate this upscaled stress strain, strain softening friction angle and also dilation angle. Based on the CNN model, then that can be fed back into the simulation. So we can use a one-cell model, as it shows here, to mimic the stress strain responses for these fine-scale simulations. That is, I think it's 100 by 100 realizations. And that has already been done. So that's a way for the whole framework of machine learning enhanced upscaling. But the key is how do we really generate the elastic and plastic upscaling properties, upscaled properties, right? So let's go back to the methodology for elastic upscaling. Or a lot of you who has taken 64 solid mechanics with me, you're already familiar with that. So basically, we have those fine scale models that is at the origin state before deformation. Then we start to apply different stress boundaries. Then it is possible for us to have those stress boundaries as input conditions. When we also have the string tensors that are outputs from flex reading, then it is possible for us to solve the compliance matrix here to really calculate the upscaled Young's modulus, Poisson's ratio, and also shear modulus, as it shows here. And we can see here, it should be different at different directions, right? And also, as we can see, I probably need to speed up. And as we can see here, we have a 20 by 20 by 20 model with 30 degree shale beddings. As you can show here, we want to upscale it into a 4 by 4 by 4 model. That means we will have, let's do a quick calculation, 5 by 5 by 5, we have 125 small grid blocks shows here. That can actually use elastic upscaling to generate the Young's modulus here, as it shows here. So what we have actually observed that the Young's modulus is going to be very different when we do the test in X direction, Y direction, and Z direction, do the triaxial shear test. So those anisotropic elastic properties is because of those shale beddings. And by only using the elastic upscaling, can we quantify those different anisotropic responses due to the subgrid scale heterogeneities, right? And also plastic upscaling, same concept, but we don't stop loading just at the very beginning until it reaches equilibrium. We will keep loading the grid block until it fails and almost reach its residual state. Then we could see that the failure mode is going to be very different, as it shows here, when we're loading X, Y, and Z direction. And also the stress strain responses is also going to be very different. And the upscaling failure criteria should actually reflect the anisotropy caused by the inclined shale beddings, right? Yeah, and we have a lot of legacy tests in University of Alberta trying to find the constitutive models for oil sands. And they have found out that the constitutive model for oil sands is not actually going to be a linear Mohr-Coulomb failure envelope. It's going to be a stress-dependent Mohr-Coulomb failure envelope, like it shows here, okay? And actually my supervisor's experiments is also there. So which provide a lot of information on the constitutive models for oil sands. And we can also see here, in order to really quantify that, that means we need to develop a constitutive model that is actually stress dependent, as it shows here, right? So only by using that, we can mimic the nonlinear stress strain behavior in the and also nonlinear Mohr-Coulomb failure envelope numerically, okay? So after we do the upscaling, we could see that when we load in X direction and also Y direction, those are just the boundaries for when it's purely sand and shale. Those are going to be the failure envelope. And we can see that even the failure envelope would be different when we load in X and Y direction. And if we look at the problem in 3D, we could also plot the isotropic failure envelope in deviatoric plane. And we could see that actually we have a shorter length here, which demonstrate a smaller shear strength when we load in that direction because of these shale beddings, right? And by using the plastic upscaling technique, it is possible for us to really plot the isotropic failure envelope in the deviatoric plane for cases with different volume fraction of shale, as it shows here. And we can see because it's horizontal shale beddings here, we can always see smaller strands in that direction. And it is also possible for us to plot the failure envelope at different confining stress, as it shows here, okay? Okay, after plastic upscaling, we need to consider about the impact of failure really on the evolution of permeability due to the shear failure. This is a pretty old slide that I show a lot of times. It's a 100 by 100 models. The permeability of each fine cell will change due to deformations, as it shows here. So as we can see here, with the increase of the axial strain, the sample will actually start to form a shear band, as it shows here. So there is going to be a high permeability flow path that is created by the shear failure. And the spatial variability of the permeability is going to be dynamic when the deformation occurs, right? And if we only consider the volumetric average, that will actually ignore difference between the change of permeability in horizontal direction and also vertical direction. And actually the change of vertical direction permeability is going to be larger because of this created high permeability flow path, right? So that means flow-based permeability upscaling is also definitely needed in our research. And Nathan has contributed a lot to develop the parallel program to fully utilize the computational power. So what we are doing here is we set the upscaling ratio and the processors that is needed. So we can automatically split the task into different cores in the CPU, so we can solve for upscaled properties. That is becoming more and more helpful. Now we get access to the clusters that has more than 100 or even 200 cores. So we can split the task, let them solve separately. Then we integrate those data together to assemble those upscaled models. So if we run a couple simulation on this geological model with 1 million cells, it will take around 100 hours to finish it. But if we do the upscaling, it would take us about an hour for upscaling and only 0.5 hours for simulation with a PC with 8 processors. Well, it's old time, 2014. So now we have much better computers with more than 100 processors. And the magnitude of simulations can be saved a lot using this parallel program, which is very handy. But still, we want to further improve the computational efficiency. That's why we need to bring the machine learning enhanced upscaling. So as we can see here, if we have 1,000 realizations for the fine scale model, as it shows here, well, if we do want to upscale the models, that means we need to do it 1,000 times. But a lot of the competitions is going to be very repetitive because those upscale regions is going to look very similar, right? So that's why we want to only select some of the representative cases to form a sizable training set. So we can run those training sets, do the local numerical upscaling elastically, plastically, and also flow-based. Then we can use that to generate a proxy model for both elastic, plastic, and flow properties. So with that, it is possible for us to further improve efficiency. And this is just one of the early studies I did during my postdoc with Dr. Rick and also Dr. Bouvel and Martin when he was in Stanford. And we conduct 4,400 numerical tests, or it could be 10,000. We just picked that number because we want to. And in horizontal and vertical directions. And as inclined shear beddings will create a very anisotropic shear strength. So those definitely there is going to be different distributions of it. Or actually this number is not created randomly. So we slowly increase that and we see this is a good number that we don't see a lot of changes beyond that. But actually when we only have 200 realizations, it also works pretty good for the training because for this case, it's only 2 outputs, which is the peak, which is the shear strength in both X and Z direction. That's why we don't need a lot of training set. And also all of the simulations follows the physical rules, right? So it is very easy for the neural network to capture actually those physical rules in very little epoch and also very limited realizations. So the inputs actually is tricky. I will explain why it's tricky. It's a volume fraction of shale and inclinations of those shale beddings, and also the ranges of in X and Z direction. This is more like geostatistical parameters for us to quantify the spatial variability of those shale beddings. So we use INN with 2 hidden layers, and those are the inputs. And we can see here the training and testing set are matched pretty well. But problem comes. So when we even have a single combinations of geostatistical parameters, we will still have those different variability of those shale beddings. And that will actually lead to different stress strain behavior and definitely different shear strengths. So that means our ANN model is not able to quantify those uncertainties in the stress strain behavior because we have to parameters the realizations at the very beginning, use geostatistical parameters. So those are the variations of the shear strength as it shows here. And now our ANN model can only give you one predictions, which is not ideal for the risk assessment, right? So that's why we decided to move forward to CNN-based geomechanical upscaling, where we can directly use the training images as an input and use that for training. I will explain later. So basically, the inputs are still the realizations in both. It could be 2D, it could be 3D. There is no problems. And we do those numerical tests as it shows here. So it could be a biaxial test in 2D and triaxial test in 3D. Then we have those calibrated inputs for both sand and shale for the geomechanical properties. And because of the different distributions and volume fraction of the shale, as it shows here, we are going to have very unique stress strain behavior for a single realization, right? So how do we really do that? So then we can use those realizations as a training samples. And the output data sets would be shear strength, which is the peak of the stress strain behavior. And also we can use the entire stress strain behavior, also the change of volumetric strain as an output. So here we only use 20 points in both X and Z direction and trying to mimic the stress strain behavior and also volumetric change curve. And we have done a lot of sensitivity analysis, and 20 points is more than enough for us to capture it, and which don't lead to a lot of changes. Then it is possible for us to train using AlexNet here is one of the most famous CNN models that is used here. So it only took us 3 minutes for training of 10,000 realizations. All the realizations is more here because now we are dealing with the much bigger inputs, because now we are considering not just the 4 input parameters, it's the matrix that is representing those input data as the realizations. And the outputs, actually, we have to generate 5 different CNN models here. One CNN model is for both the shear strength in X and Z direction, and also the stress strain behavior in X direction, stress strain behavior in Z direction, and stress volumetric change in X direction, and volumetric change in Y direction. When we load in X and Z direction, volumetric strain would be the same. It's just if we look into details, we only show the 50th percentile, which is the average performance for a CNN model, which is pretty good. And we also observed that the R square, even the lowest amount, which is like P10, is over 0.8, which is pretty impressive, as it shows here. So the blue dots actually the training sets, and the orange dots are actually the testing sets, which works pretty well. And then Maggie Xiaoyan actually, as we mentioned, we cannot directly use CNN models into the simulator. So we have to use those CNN predictions and trying to still back calculate the constituted models that we are going to input into the simulations. So it's pretty straightforward analytical method that we used a lot, and we can calculate the Young's modulus, Poisson's ratio, based upon the inclinations of this elastic stage, and also the peak friction angle, and also peak dilation angle, and also the string softening table, as it shows here. Okay, I explained very, sounds very easy, but it took her a while to figure it out. And it works pretty well. That it is possible for us to use just one single cell to model, to reproduce the fine-scale geomechanical responses. So here, the fine-scale simulations of finite volume method using Flux 3D, it shows in red dots, as it shows here, red curves, as it shows here. And actually, the CNN proxy prediction fitted well. Yeah, we already showed the R-square for it. And the upscale one-cell model also match pretty well for both when we are loading in X direction, when we are loading in Z direction, the stress strain behavior, and also the change of the volumetric strain. That actually gives us a lot of confidence that our CNN-based upscaling definitely works, using only one cell to represent the 100 by 100 grid block, right? Okay, so very numerical up to now. And now we're trying to find experimental proof with the system by Reservoir Geomechanics Research Group. Actually, Dr. Rick and I have a student, Bingyu. She is trying to find out, okay, so whether our upscaling techniques will make sense experimentally. So Nathan actually helped to design the transparent cell. The reason why we want to make it all plastic and carbon fibers, we want to put the traxel cell into the CT scan, so that won't cause a lot of reflections, right? And also, now we even find out that, oh, maybe the traditional traxel shear won't be a good study for SACD. It might be traxel extension. And she, Bingyu, is actually driving this forward, trying to visualize and investigate the coupled flow to mechanical behavior of IHS. And also, it is possible for us to visualize the pore structure changes of IHS during traxel compression and extension test by using this workflow. That is really important. And we're also going to move from a direction that is studies this numerically. I know Dr. Rick mentioned, oh, why don't you use 3DEC? Oh, we started with PFC first and trying to see how it works. And we reproduce a model using PFC. Actually, Xuehan did this. She is sitting in the back and using those mud layers that has smaller grain sizes and those sand cells with bigger grain cells. And she also used a smooth joint contact between the sand and mud. So we can possibly model the slip between the sand and mud layers. And we also took the results that Masood has done back in 2022 in his thesis. And she is able to actually match, or kind of match the stress strain behavior and also the permeability change using these PFC models. And she also integrate her acoustic emission code that actually we want to use this to trying to study the crack initiation and also the evolution of failure modes during this process. And as we can see here, there is a lot of cracks that is formed within the mud layers. And also we can see quite a few slip along these shale beddings. So yeah, it's still ongoing work. Xuehan was here for just 8 months. She has been progressed very fast. And she is going to lead this research and hopefully bridge the gap in upscaling technique that we can both consider the lithology heterogeneity, which I have been working on previously, and also discontinuity. Okay, now let's move to more realistic cases rather than those theoretical studies, which is multiphysics. So yeah, this is a model that we generated for geological models for oil sands, and it's 2.4 million cells, which is very fine scale, and this is just for one cell, one well pad in pad C in St. Mackay River, and we could see the shale beddings in both the Wabsco member and also the macrame formations, as it shows here. And we utilize the sequentially coupled platform that is designed by Nathan and Abel. And it is possible for us to consider both the pore pressure changes that will lead to deformations and failures in the reservoir that also cause the stress and strain-based permeability and porosity changes that will feed back to the CMG. So it is possible for us to generate a reservoir model that includes both the Wabsco member and also the macrame formation, where we could do the sequentially coupled simulation. And for Teal Clearwater, which has the caprock or overburden, it will only be used for geomechanical simulation. That is the same case for the underburden, which is a Devonian formation. And as we can see here, the steam chamber propagation can be well modeled, as it shows here. That also leads to permeability evolution as a function of time. And also it is possible for us to visualize the steam chamber propagation both over space and also permeability evolution over space. So it is a very complex thermal, hydro, and mechanical interactions. So as we can see here, it is possible for us to model the non-uniform steam chambers formed due to the shale beddings, as it shows here, and also the deformation caused by the pore pressure changes and thermal expansions during the SACD process. So now it's about time to really use our upscaling technique, and this actually shows the upscale models that can match the fine scale model pretty well for both the steam chamber propagation for the fine scale simulation. And what is really important, we decreased the simulation time by 94%, which is really huge. And this is showing the comparison between the temperature, it's well matched, and also pressure, it's well matched, and also the oil saturation is also well matched. And also it is possible for us to match the shear strain and also the surface heat, as it shows here. So then it is also possible for us to match the cumulative oil production and volume change between the fine scale and upscale models. So what is really important, we can actually use this upscaling technique, now dive into the research of the caprock integrity during SACD. So as it shows here, we have the upscale A shale, which is a very continuous shale. And above that, I didn't show it here, there was an even thicker Clearwater shale, which is more than 30 meters for this case. And there's also a fine sand, which is Wapska sea sand in Mackay River. And also there is a very thin Wapska D shale, as it shows here. So it is possible for us to generate a factor of safety for different layers of caprock as a function of time and also the space. So as we can see here, the minimum factor of safety, though we only pick the minimum factor of safety for conservative here, as we can see here, for bottom of Clearwater shale, which is the top of Wapska A shale, actually, when we do the steam injection for more than 4,000 years, you can see here the factor of safety is well above 1.5, right? But if you look at the bottom of Wapska A shale, you could see that the factor of safety is almost the drop to 1. Well, which is not that bad because the Wapska A shale is really the first important caprock in the Athabasca oil sands. And the Clearwater shale will provide another layer of caprock for operations, right? So actually this will be more important for us to look at because we actually consider the bottom of Clearwater shale, which is as a more safer, a more thicker caprock here. And by using these upscale models, it is also possible for us to run a lot of simulations with different injection pressure. So as we can see here, we have a gray plane, which is factor of safety equals to 1. Then this is a red responsive surface actually show injection at the operating injection pressure, which is history matched. We can see here the factor of safety is well above 1.1 at the bottom of Clearwater shale at all time and space. But when we increase the injection pressure to 1400, we could see some critical regions that are not safe, as the yellow plane shows here, after 3,000 days of injection. And when we keep injecting the injection pressure to 1600 kPa, then we could see some critical regions that are not safe after 1500 days of injection. So this responsive surface of factor of safety is an informative way to illustrate the caprock integrity at different locations and also time. And it is very useful to optimize the injection pressure at different locations and time during SACD. And we just skip this slide due to time. And this is our future research that we want to do. And right now we are trying to looking at the enhanced oil recovery in iTrust. So we want to trying to test whether the cavity expansion would be a good option for it, which I won't dive deep because of the time constraints. Okay, now goes to the decision-making for subsurface energy development. So as we all know, there were more than 25 proposals that they are trying to develop a lot of CCUS hubs beneath our foot, right? And the Pathway Alliance was just they submit that their formal application yesterday to Alberta Energy Regulator, and it seems like they are very serious to develop that. And this is actually we had the privilege to with the mentoring by Dr. Teletonic, that it's possible for us to do the uncertainty quantifications for one of our future energy system project. So we use Aquastor CO2 storage project as a case study, and Walid has been the key person driving this research. So the study of the uncertainty quantification workflow would be generate the 3D flow model and also generate the 3D mechanical Earth model and run the couple of simulations at the very beginning and generate the proxy models, which I'm going to explain later. Then it is possible to have a lot of realizations with different plume shape and different plume area. Then at the current stage, we didn't find a great way to treat it in 3D. So we actually overlap all of those CO2 plume vertically and find the maximum plume shape. That is when we see from the top. Then it is possible for us to, if we do have the seismic interpretations, it is possible for us to reject the realizations that is outside of the predictions of the seismic interpretations. So the proxy models would be, after we run the reservoir geomechanical simulation, we have outputs for both the CO2 plume, pressure, volumetric strain, and vertical displacement. And he used the RUNet to generate the proxy models. And after model tuning, it is possible for us to match both with the proxy models with the simulations, which as it shows here. So this is a proxy model where we inject pretty aggressively after today, which is 1 million ton of CO2. We want to see the variations of CO2 plume. This is just for a case study. We want to show the capability of proxy models. That's one of the reasons why we are injecting very aggressively. In our simulations, I don't think that will be the case in reality. They won't do that. And as we can see here, the proxy model actually matches the simulation pretty well. And also the residuals, we could see a little bit variations nearing the edge, but still it is fine. And we could see that with those different realizations, this is P10 and this is P90, we could see there is a huge variations of the saturation predictions for the proxy models. We actually replace a fictitious observation well that is, I think that is around 1 kilometer away from the injection. I know the original observation 1, which Walid considered observation 1, which is just very close to the injection well. And it is possible for us to observe that using the fictitious O1 as an observer. I think that is around, yeah, very close, 1 kilometer from the injector. And we could see that in this particular case, when there is no structural continuity exist in the simulator, so we can see very fast pressure evolution as it shows here for different cases. And that is the same for geomechanical and responses, which both the subsidence and volumetric strain because of the pressure dependency. And that's also the pressure evolution. As we can see here, the variation won't be too big because of only we consider the spatial variability. And that's the same case for vertical displacement. And we probably need to dig deeper into the geomechanical variations because right now, the input for the proxy models is only permeability variations. We didn't consider the variation of geomechanical properties and also the structure uncertainties. And we can convert the plume area. We already mentioned that to stack that together. So we have estimation of a plume at a given time step. And we use the rejecting sampling to reject these realizations that gives very way off predictions compared to the ground truth model that we have, which will be, if possible, will be the 3D seismic interpretations. Then Walid actually I think he generated a model based on 1,000 realizations. And then the proxy model would work as we showed before. And then he generated another 10,000 geological realizations serve as a prior. And we didn't directly run those 10,000 realizations because we know each simulation will actually take 20 minutes, even we use the non-isothermal conditions. Oh, sorry, isothermal conditions. If it's non-isothermal, it will take even longer. Then if we run those 10,000 cases, it will be 140 days. But by using the proxy model, only take 80 minutes to really have the outputs of those 10,000 geological realizations. So the computational time for data-driven model is less than 0.01% of the physics-based simulations. And by use the rejection sampling here, as it shows here, only 9.2% of the realizations eligible after those uncertainty quantifications. So we reject a lot of realizations that won't be realistic according to the monitoring data. So in the future, we are going to keep grinding on this direction, which is data-driven modeling, optimization, and decision-making system for subsurface energy development. This is an NSERC Alberta Innovates Advanced Project with both Dr. Chalatonic and Dr. Bovell. Hopefully, we can have a lot of results with Gary's joining us, and also 2 PhDs. We also two postdocs will join us in the research. So, yeah, that's summarize my presentation today. So what is actually multiscale and how do we implement that upscaling technique into multiphysics simulation, and how to really further improve the computational efficiency, use data-driven decision-making. And this is my acknowledgement. Thank you all the sponsors, and also Dr. Rick Chalatonic, Dr. Chip Forwell, Dr. Nathan Daisman, Dr. AJ Ganesh for the contributions of the work. And also Walid has been the key drivers for the uncertainty quantifications for CO2 storage. And that is actually the paper he presented in SBCT, which is just 10 days ago. And also Dr. Martin Marr. Now he moves from Stanford to Los Alamos National Lab. Thank you for his contributions for machine learning. And that's it. Thank you.